Hello and welcome to the lesson on thin film interference. So today's goal, I want you to be able to explain the concept of thin film interference. So by the end of it, you need to be able to explain to me what it is. And then I want you to be able to tell me some of the applications and be able to do the appropriate calculations. So let's talk about what it is. So whenever you have, you've seen interference before. So if you've seen in soap bubbles, when you get that kind of color effect, or when you've got spilt gasoline or oil on the ground, and you get that neat kind of color spectrum, that is in fact what we call optical interference. So why does optical interference occur, or how does it actually happen? We've got a couple of possibilities here. So you can see that my slide, I got to fix it just a sec. They're all fixed. Sorry to keep you waiting. Hope you weren't sitting there too long. I know you weren't. So some light can be reflected. So what we're looking at here, just to clarify before I get into it, what we're looking at is basically your air interface. Then we have the film. So this could be either be soap, or it could be gas. Wants to keep highlighting for me. Okay, so it's that thin film. And then underneath, for this example, I've got air, but it could be water. It could be whatever it's sitting on top of. So light comes in, and option number one is that the light gets reflected. Okay, so that's option number one. The second one is some of it gets refracted. All right, so now that light enters the film, and because it's a more optically dense medium, light would bend. Now, at this second interface, there's two options. The light could exit underneath, like that, or it could be reflected back up again, which means it would be exiting like that. All right, so we have a combination of things that can happen. So the end result, or the one that we're interested in, is the combination of these two above the surface. So if we have light that does this kind of rebound, we now have, draw my really cool looking eye. There it is, a little bit creepy, but that's all right. We're going to have light reaching the eye that was reflected from the thin film, and then we're going to be having light approach our eye from the reflected, transmitted light as well. What happens though in this time frame right here, or this distance, this delta L, the light waves, these ones here, have actually traveled a longer distance. So what does that mean? Delta L causes light waves to go out of phase. All right, so that delta L may cause the light waves to go out of phase. If they go out of phase, then we end up with some form of destructive interference when it reaches our eye. And that's what we're keying in on today. And just to finish that diagram off, there's that light underneath that got transmitted. But it's the light that's above that we're most interested in. So we're looking at those possible scenarios. So in the note, likely didn't come out very good if it's printed in black and white. But that's that distortion that you see with thin film. So if you're out blowing bubbles in the summer, because I know it's how a lot of you pass your time sitting on the back porch blowing bubbles that you got from grandma. But that distortion that you see in the light, that is that thin film interference. All right. Also, if you've ever heard of Newton's rings, what it is a bowl of water set on top of kind of reflective glass. You get that same kind of distortion going, but when you look into the bowl, this is your result right here. You end up with a series of rings. And it's the way the light is reaching or striking your eyes for constructive and destructive interference. So just a quick review on the basics from grade 11. We talked about fixed end. So fixed end, if I send a pulse toward a barrier, then what happens? Well, that pulse, I guess put an arrow on it. What happens then is the pulse is reflected underneath. I'm not worried about the transmission part of it as of yet. So we're just looking at the reflection property of reflected waves. So fixed end is reflected on the opposite side. Free end, put my ring so it can go up and down. If you recall from investigation, it gets reflected on the same side. That's going to be important for us when we get into our analysis here on the next slide. So, 3 cases for our thin film interference. Okay, let's look at the situations here. So let's say that the thickness is less than the wavelength. So let's say that the thickness of the film, so I'm looking at, here's my thickness, T, in each case, okay? So when you see the thickness, that's what I'm referring to. I know the thicknesses, I increase them as we go because we're going to make them a little bit thicker. But let's say that the thickness is equal to, or approximately equal to 0 lambda. So very, 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 very small thickness. All right. So what happens is that incident light strikes there. We get our reflected light. And then here comes the drawing challenge here. So I'm just going to put a kind of a dashed black line there. So let's talk about the light that enters and exits the film. So it's going to be refracted down there, there, and transmitted out. So that's where I'm going to start the waves here. So if there's been kind of a zero distance lag here, so that means the light wave that went into the film, okay, this light wave here, because it was virtually 0, okay, that means that the distance, the time lag is virtually the same. So I'm going to start with at the center line and produce my sinusoidal wave. Now the blue one, let's just take a look at it. Let's take it from the example of it entered as a crest, let's say. So right here it entered as a crest. When you transmit, it doesn't reflect, it doesn't change, it's still a crest. When it strikes the back surface, it's like a fixed end, it's going to become a trough. So as it comes out, or comes out here, it now transmits as a trough. So that means that it actually starts and looks like this. So that means that it is actually reflected out of phase. This results in destructive interference. And this is all because of this right here. The distance is virtually 0, so there was no time lag. So we're saying that they got to the start line at the exact same moment in time. That blue wave, though, however, because it struck the back surface like a fixed end, it got reflected, okay, out of phase. So it changed the direction. So if it was a crest, like I have here, I have it kind of going to a crest first. It's going to go to a trough. So we have complete destructive interference. If we increase our thickness a little bit, so the thickness now becomes a 1/4 lambda, comes in, we're going to have this up to here. Same thing, I'm going to draw a dotted line just for a starting line. All right, so the green line is right there. I'll make this one blue. So what is the difference here? Well, same thing. Let's say they both strike as a crest. So right here, it's a crest. That means this green line is going to start as a crest, or going up to a crest, I should say. So there we go. Now the other one, following the other path, so it struck here as a crest. It came back here, got reflected, so now it's a trough. It's going to exit as a trough. However, it's gone a 1/4 wavelength. All right. So if it was a trough, it means that it's going to look like this, go to the trough, but we've moved a 1/4 of a wavelength. Okay, we've moved a 1/4 of a wavelength. So if that's a full wavelength there to there, there's half, there's 1/4. All right, so that means that we've got a bit of a shift going on. All right, so that means if we go back and that delay has occurred, it's actually now exiting that 1/4 delay. So we have that 1/4 delay. But now remember, the thickness is a 1/4 lambda. The thickness is a 1/4 lambda. So that means to go there and back, it's actually traveled half lambda, okay, because it's gone there and back. So it's out of phase by a half. So back up to my diagram up here, it's reflected as a trough, but this much of the wave has occurred in this distance. So now it's going to come out at the starting line as a crest. Okay, because it's traveled a half wavelength longer, it's kind of undone that reflection. Now we have constructive interference. All right. Then when you go to the next thickness, so it had to travel all the way there, and then out to that kind of starting line that I'm using here. It's just to help with the visualization. So we strike as a crest, so that means it's going to go like this, our green wave. That hasn't changed. My blue secondary wave, it's going to go to the back. It is now been switched out of phase, so it crests, it becomes a trough, exits as a trough. However, it has gone or traveled half lambda there and half lambda back, so it's really gone an extra lambda, okay, which means that it is now 100% out of, or it's gone one whole wavelength, I guess you should say. So if it was a crest, became a trough, it's going to be a trough because it's going to be one whole wave cycle in there, which means that we return to our destructive interference. All right. So it's just playing with reflection on a fixed end, and then it's talking about how much of the wavelength has occurred, that extra distance it has traveled. All right. So we get this pattern of 0 lambda, 1/4 lambda, half lambda, connected with constructive and destructive interference. So then when we go to the summary here, we know that constructive interference is happening every half lambda. Okay, so constructive interference right here. The next one will be at 3/4. All right, our destructive interference started at 0 and happened at a half. So when you go and do kind of the calculations for this, so constructive interference is equal to lambda over 4. That's the first time it occurs, plus every half lambda. And then we put on the equation, or to fill out the pattern, is this n minus 1, because the first max occurs at lambda by 4. So if the first max, if n is 1, the first max, this would be 0. This term goes to 0. Oops. So that means your answer would be lambda over 4. So this is your general equation. This is the pattern that you get, and it's just y equals mx plus b. It's a linear relationship. Okay, your y-intercept. Here's your b, and here's your slope. Oops, this is your slope. N minus 1 is the x value. So when you simplify that, join it together, so we get lambda over 4 plus 2 lambda, n minus 1 over 4. Getting a common denominator, I'm going to factor out the 1/4. We'd have lambda plus 2 lambda n minus 2 lambda. Simplifying it, it becomes lambda 2n minus 1 over 4. Okay, and n is the maximum. All right, so I'll move on and finish the rest of this note in our next video.